We're trying to find the moles of CO2 produced during combustion if we know that 1 megajoule of heat is released during that process. So we basically have to set up some equations for each one of these different fuels. So we'll try doing this one like CS plus, we need O2 gas for the combustion here. And because there's no H's, it's not a hydrocarbon, then we know that we're just going to have CO2 being produced as gas. And this is an exothermic reaction, so we have the heat being released in negative form on the right side. So we'll do that for the other ones as well. CH4 gas plus the, we're just going to balance this right away so we don't waste too much time on this. But essentially the next step after sort of writing these out is to just balance it. And we're going to have CO2 gas plus 2H2O. This is a gas, and then minus that H over there. For this one, it's just going to be C3H8 gas plus 5 O2s, and that'll become 3 CO2s plus 4 H2Os. And it is important to keep track of these states if you want to get the correct enthalpy of formation for them. So this is actually given in some chart, but we're going to be doing that in the next step. And then we're going to do 2C8H18 gas plus 25 O2. And that will become 16 CO2 plus 18 H2Os. And then we have the minus enthalpy. So from here, we can actually rearrange these equations by saying that the enthalpy of the reaction is essentially going to be equal to, the total energies of the products minus the reactants. And so now we have to kind of go through and figure out what the formation enthalpies of all of these different things are. So we know that these two things are actually in their natural state. We're just going to give them 0 energy is necessary to form those because that's just naturally found that way. But from the list, we're also given that the CO2 is negative 393.5 kilojoules to form 1 mole of CO2. So we're just going to put that right there. That's the formation enthalpy to create that CO2 gas. We're going to do that also for the CH4. And so that's negative 74.6 kilojoules. The O2 gas is still 0. The CO2 is always going to be this value here. And then the H2O is, well, we have 2 moles, so we have to multiply that number that we get by 2, but we got 241.8 kilojoules, 241.8 kilojoules. And then there's 2 of those, of course. For this one, I think we have negative 103.8. This one's 0. This one is 3 times 393.5. Here we have 4 times 241.8. And over here, we've got 2 times, this one was given to us, I believe, so 250.1. And then we also have 24. This is just going to be 0, though. And over here, we can do 16 times negative 393.5, 18 times the negative 241.8. And now we're basically ready to head into the next step, which is going to be to solve for the HRXN. And you can even put a little RXN in here because this is the enthalpy released in this reaction, or the heat released rather. But at the constant pressure, the heat is the enthalpy. So let's calculate the HRXN for just a coal. I mean, this one's easy. It's already kind of, this is just 1 over here, so we don't really have to do anything. We're just going to rearrange the equation, and we should just see that as negative 393.5 kilojoules. For the next one, we have to do a little bit of math here. So let's get the calculator. And so we're essentially just going to take our negative 393.5. We're also going to subtract 2 times the 241.8, and that's going to give a total of that much energy on this side, which is the product side. Then we're going to subtract the reactants, but the reactants are negative, so we have to actually add those with 74.6. And so we get the total energy for this one is 802.5. So RxN is negative 802.5 kilojoules. For this one right here, let's add up all these energies. So that's going to be 3 times negative 393.5. And then you would technically have plus 4, but there's negative 241.8. And so the total energy on this side, on the product side, is negative 2,000. But then we're going to add we'll subtract the energy that's negative from the reactant side. So like this works out to be plus 103.8. And so we should get that this third reaction has negative 2043.9 kilojoules. And for the final one, let's start with this. We got 16 times negative 393.5. And then we can do 18 times negative 241.8. So it gives us a total of that much on that side. Let's go ahead and, this is supposed to be negative over here, but we're going to add that stuff in there. So 2 times the 250.1. And so we get a total of about 10,000 here. So negative 10,148.2 kilojoules. Now the goal is to be able to achieve the moles of CO2 produced, and we need some kind of a conversion factor to get there. So let's just go ahead and take our RxN that we discovered, and because this is going to be in joules, right? And then if we know that we're given, this much energy, a megajoule of energy applied, or this is how much was released in that process, really, then these things will cancel out and we'll be able to left with the moles of CO2. So the HRXN for that one was 393.5. So let's take our megajoule and let us divide that by the 393.5 e to the third, because it's a kilojoule, and we're left with 2.541 moles of CO2 produced in the first reaction. Now in the second reaction, we kind of already have the setup. So we got the joules here. We're going to need the conversion factor from the second one. We notice it's still 1 mole of CO2. 1 mole of CO2. And over here, we know that this is actually supposed to be 802.5 e to the third joules for the RxN. So that's just going to give us 1 e to the 6 divided by 802. And you get 1.25 moles or so. 1.246 moles of CO2 in the second reaction. In the third reaction, we have the same amount of energy. And then now, though, let's look at the conversion factor here. We have 3 moles of the CO2. And then this is going to be the delta H on the bottom, which is 2043.9. So now we can do that one. 1 e to the 6 divided by, 1 e to the 6 times 3 divided by 2043.9 e to the third, So we get 1.468 moles of CO2 in that third reaction. And then in the final one, take 1 e to the 6 joules. And then the heat for that one was 10,048.2 e to the third. And the conversion factor here was 16 moles. So we have 16 moles being produced in this reaction with that much heat being emitted. And that's going to give us CO2 right there. So 1 e to the 6 times the 16 over 10,148.2 e to the third will give us 1.577 moles of CO2 created at that point. And so that would be the answers.